to a less dense medium, like water to air. And so as this occurs, the light starts to bend by greater and greater angles. And 1, let's say, is equal to 1, and 2 is equal to 4/3. I'm just using these same examples here so that the numbers don't change, and we're just changing the basic principles that we're looking at. So as we continue to increase this angle here, theta r, becomes greater, bigger and bigger than the incident angle. And so that means that eventually theta r is going to go to 90 before theta incident goes to 90. So that means that you can still have light coming in, but then you have an angle of 90 degrees here. And what that tells us is that no light can enter the less dense medium. And that's what happens. And because no light can enter the medium, it all must bounce back. So this is an exception to that rule. Remember we said before that in most situations, you're going to have a reflected and a refracted ray. But here's an example of where we don't get that. This is the critical point for total internal reflection. Okay, so we get to a little bigger angle here, slightly larger angle. Then it bends even more, so this is almost 90. But then we get to that critical point, and we call it the critical angle because it is that critical point where the light goes right along the surface. So this becomes theta refracted. So when this condition is met, we call theta critical the critical angle. And so the condition on that is N1 sine theta critical equals N2 sine of 90. So we're starting in this medium. This is the source now. We're going from more dense to less dense because we're saying here N2 is the index of refraction of water, N1 is the index of refraction of air. So you know that it's bending away from the normal. And so when it gets to that critical point, then that's the minimum angle that will produce total internal reflection. Not the only angle, but it's the minimum one that produces total internal reflection. So let's go ahead and figure out what that would be for this example. And let's apply it to the following situation. Say that we have two fishermen that are on the far side of a big lake, and you are down here on the bottom, and you're looking up through a mask, like that, at the light that's coming from the sky. Okay, and so I don't know if anyone has ever tried this before, but if you look up, say from the bottom of a swimming pool or from the bottom of a lake, or you're snorkeling in the ocean, what you'll see is kind of a big blue ball up there. It won't take up the whole field of vision of the sky. So basically what you're doing is you're taking light that's coming from the upper half plane, it's bending at the critical angle like this, and then down to your eyes. Like that. Okay, so that is, and then anything that is a steeper angle than that is going to result in total internal reflection. So if you look at angles that are bigger than this angle here, which I'll call 2 theta, then any light that's coming in at a steeper angle from this critical angle, this is theta critical here, this is theta critical. Anything that's coming in from at a steeper angle than theta critical, this is theta greater than theta critical, that produces total internal reflection. So that if you look away from the big blue ball in the center of your field of vision, what you'll see is reflected light that's coming off the bottom and then coming back down to your mask. A lot of people have never seen this, not because you haven't had the opportunity to, but because when you look up, water tends to go down your nose. And so that is uncomfortable, and people don't want to experience that. But if you were to do that, or you've got masks where you can pinch your nose up, and then you just look up, just check it out next time. It's kind of an interesting thing. And so let's ask then, through what field of vision is necessary for you to look to see the whole upper half plane? Now it'll be in a distorted form. You may not be able to see the fisherman here waving at you because you're taking all of this light and you're compressing it down into a steeper angle. And this, by the way, is one of the reasons why you can get really sunburned if you're not too far below the surface. If you're just like swimming around near the surface, you're getting this concentration of the rays that are coming from every direction, coming down with more intensity. And so you go on a trip to Hawaii or something, you can wreck your whole trip just by swimming around near the surface for a few hours. And then you get horribly sunburned, and then you're not feeling good for the rest of the trip. Okay, so that's the question then that we're going to ask here, is let's find the critical angle, and then let's ask through what angular range can you see the upper half plane? By upper half plane, I mean 180 degrees of sky. And let's assume you have a good horizon view so you can see the whole sky. You wouldn't have any mountains or anything. It would just be the whole sky. And then it would look like a big blue ball, but through this much smaller radius. Okay, and so what we could do then is we could say, well, in water, sine theta critical equals in air sine of 90. Because we know that's the expression that we use to get the critical angle. So then we can go sine of theta critical equals in air divided by in water. And then the sine of 90, of course, is 1. And so what that will give us, and by the way, if you do this and you end up with an angle that is, or a sine of the angle that's bigger than 1, what it tells you is that you got these two things mixed up. Because you're not going to get a sine of theta that's bigger than 1. That is the forbidden territory over here. That's when you can't solve the mathematical relationship, and so the refraction relationship no longer works. Okay, so that is just a quick way to check that you're doing this right, because if your calculator says error, it means that you got in water on the top somehow when we were setting the equation up. Okay, and so then all we have to do from here then is to solve for theta critical. So that's the inverse sign of 1/4, which is the same thing as the inverse sign of 3/4. I think it's something like 48 degrees. .59 degrees. Okay, so if that's the case, then we haven't quite solved this problem, but we've gone a long way to solving this problem. To what angular range are you going to have to look then to see the whole upper half plane? Anybody?
Positive negative 48 degrees, or you would say we would do 97 degrees.
Good. It would be double that angle. This would give you from basically 0 to 90, and then this would give you 0 to minus 90. And so it would be 2 times theta critical. Okay. So that's the angular range you have to look at, 2 theta critical. And so that, yeah, it would be about 97 degrees. So you're just looking through just a little more than half of the angular range that would give you about half the sky if you were up here on the surface. But you're seeing the whole thing, but with a slightly distorted form, because you're taking all of this light and all of that light and you're bringing it in through a steeper range of angles. So again, that is a great way then to get a sunburn, is to just, your skin still feels cool, and so you don't notice that you're burning. But you're near the surface, so you're not losing that much of the intensity of the light. You might have to go down 33 feet before you lose a significant amount of light intensity. So, you know, on that first day in Hawaii, you know, just wear a shirt or something.
So you get burned more significantly just underneath the surface because all of that concentration of light is in you than like in the air?
Well, you're not going to feel the burn. That's the problem, is your senses aren't giving you a clue that you're in trouble. Like if you'd feel pain, you know, if you were just laying, or most people would. Some people just love that sun, they don't know until the next day. But normally you feel a little bit of discomfort, or maybe like something is starting to crinkle a little bit and crack or bleed or whatever. But you're not going to notice that here because your sensors are shut down and you're just feeling that cool water. Any other questions? All right, so with that idea then in mind, let's go back. There. And here's some other examples of total internal reflection that I wanted to show. One is this mirage. Okay, and so this could also be a mirage of a pool of water. Okay, but here, essentially what's happening is, as the light comes in, it bends, because you're going from less dense to more dense, what's happening is the light is going to tend to bend this way. Okay. And so, by the time that we get to here, though, this is the point when you finally get to total internal reflection. And so then from here on up, the light tends to bend straight up toward your eyes. And so essentially then what you see is an inverted image, in this case of the palm tree, that's below the ground. Another example of this would be in a car. If you've ever been driving along a hot road, you may see an inverted image of the car below the surface of the road. And here's the car ahead of you, way ahead of you. And then, okay, so how does this light tend to want to bend? Well, we're going from less dense to more dense. Okay, so it tends to bend up here. Well, normally it would tend to bend toward the normal, but in this case, it bends away from the normal. So the reason for that is that this is superheated air. Near the surface of a desert, or also here near the surface of the ground. So the air normally gets more dense as you get closer to the surface, but near the superheated surface, we have less dense air. Because it's hot, it's being cooked by the asphalt surface, and that makes it super hot, and being hotter, it spreads out more and isn't as dense. And then up here we have more dense air. Okay, so when we go from more dense to less dense, it tends to bend away from the normal, like this. Right? That was what our rule was before. Bends away from the normal when going from more dense to less dense. But then finally you get to this point, this is the critical angle, so you get total internal reflection at that point, and then it starts bending from less dense to more dense, which continues that same curvature up to your eye. Okay, so then you're looking, say, from your car, and you're seeing the virtual image of this car that's ahead of you, flipped upside down, like that. So have you ever seen that, like going out in the Mojave Desert somewhere, super hot, and then you look way up on a straight road, and you see what looks like a kind of a ripply image of the car that's below the surface of the road? That is the kind of thing. That is another example of a virtual image that's caused by total internal reflection. Yeah.
And this, like you said, it's a typical relationship with heat. Is this because the hot road creates the less dense air?
Yeah.
Less dense?
Right, and so it's a local effect that will only occur if you have an anomalously hot surface, because usually the pressure will decrease with elevation. And here, locally it increases for a short time, but then it starts to decrease again once you get away from the hot surface. Right. Any other questions? Okay, and then finally, I think our most classic example of this is when you're dying of thirst out in the desert. And then you see this beautiful blue pool of water. So you start running for it. And then you start stuffing, because you're delirious, you start stuffing your mouth full of sand, thinking that it's water because you thought you saw water. But no, you're actually looking at light that's coming from the sky. So when you see this blue pool, this is a virtual image of the sky. Now there are real pools, of course. So, I mean, this isn't necessarily a mirage, but quite likely could be. And so here's the light then coming in from the sky, because the air is so hot, bends away from the normal, and then back toward the normal again. And then your eye extrapolates along straight line paths to produce the pool. And so as you start moving toward it, it gets kind of frustrating because the optical situation is such that the pool will always stay that far ahead of you. So you go, oh, I thought I was there. But no, now it's way over here. And so now it's this light that's coming in and then coming up to your eye, and then you're extrapolating along. And so that could be another clue. If you see that you don't seem to be getting any closer to it, then that could be an indication that it's not real, and that maybe you better just consider marriage. Any questions about that? Okay, now this kind of total internal reflection is also used in optics light fibers. And it's a basis of basically the internet. Because if you're sending information through wires, you have to heat up the wire as you send the information through. And so that means you need a bigger wire to handle the heat. And then you're losing energy while that's happening. Okay. So what we'll do here, we'll notice if I shine it through this bent piece of plastic that it keeps bouncing because the way that the thing is set up is such that you're always greater than the critical angle. And so the light then is trapped to keep bouncing back and forth within this thing. However, if this were a real optics light fiber, you wouldn't see any light until you got to the end. This is demo light fiber, and we want to see the path. And so that's why some of the light does interact along the way to impurities in the path. It's a learning tool, but not so much as a practical thing. So then here we can see with slightly less extreme curvature how it just keeps bouncing until it comes out on the other side. So you can send this information essentially at the speed of light, and you don't have to have a really big light fiber because you're losing very little energy along the way. Do it for a straight one. So you get this thing set up so that the geometry of this is such that you're always greater than the critical angle so that you get total internal reflection. So then if you don't have a bounce at all, it just goes straight through. But the extra time that it takes to go along that jaggly path is insignificant because light can travel around the Earth something like 7 times in 1 second. For the critical angle. So the critical angle is just the ratio of the indices of refraction, as we said before. And then here is one of those optics light fiber tubes that allows for the light to travel along that path. Are there any questions about that? Okay, next, what I wanted to do is look a little bit at mirrors and how curved mirrors can deflect light.